Good afternoon, everyone. It's my real pleasure to have the opportunity to present some of the work we have been doing. And what I will try to do in the upcoming 15 minutes is give an overview of some hydrogel work we have been doing for biomedical applications. So I'm a polymer chemist from training, but I will try to explain some concepts of materials that we have made and also how we can process them in 3 dimensions. But I also have some extra slides which, if wanted, can be discussed in the upcoming days as well. So for those people who don't know Belgium, here we are, nicely squeezed in between France, Germany and the Netherlands. And for those people who did not yet visit Ghent, some people in the audience did, I know. It's a very nice and historical city center, so if you're ever visiting the area, I would say let me know and I would be happy to show you around certain places. Now, our research group is the Polymer Chemistry and Biomaterial Research Group. We are located in the Faculty of Sciences, the Department of Organic and Macromolecular Chemistry, and there are actually 3 research groups that are doing polymer chemistry work. And we are actually unified under the umbrella of CEMAC, the Center for Macromolecular Chemistry, all devoted to polymer research. Now, what we specifically do is we, for certain medical applications, try to develop certain polymers or building blocks. We process them in 3 dimensions, producing certain scaffolds from which drugs or other bioactive compounds can be released. And in some cases, we still apply a unique coating to make those materials cell interactive or more friendly to the environment. And what we have been doing in the last couple of years is developing polymers for orthopedic applications, developing polymers for nasal stent applications, cardiovascular stents, and also here below, through electrospinning, making polymers for wound dressing applications. And again here, at the end of my presentation, I will very shortly give some possibilities that I would see for possible collaboration with different universities from within the country. And I think the field of wound dressing and the release of certain bioactive compounds is certainly one way to go. Now, as I mentioned during the opening ceremony, we have collaborated before and welcomed quite some people from your country, Diana Giol, Juana, organizer of this conference, and also Diana Mogosano has been working in our lab. And once again, I hope that during this conference we will open up discussions to also intensify this in the upcoming years. Very sensitive pointer, so I'll try to be careful. So, what I will talk about today is a very specific type of polymers which we call AUP. I'm a chemist, some of you are not, so no worries, I will not bother you too much with heavy chemistry, but let me try to explain a couple of things of what we have been doing. If you look at polymers in the medical field, there's a huge amount of polymers available, biodegradable polymers used for suturing materials, biopolymers such as alginate and others. In our work, we have been focusing on polyethylene oxide, which is a material which is approved by the Food and Drug Administration, being already a good prerequisite for selecting this material for future biomedical or pharmaceutical applications. And of course, some of those structures can also be developed in different types of polymer architectures, where their biological activity will be completely different in the long run. Now, if you try to summarize the polymers used in the medical field or in the pharmaceutical field, then they can actually be divided in 2 main classes. Hydrogels on the one part, very hydrophilic materials that take up huge amounts of water without dissolving, and then the non-water soluble compounds, which are polyesters and others that also find various applications. Now, hydrogels date back to the 1960s, so already more than 60 years, a lot of research is being done on these types of materials. So first, something on the polymers. Our research group had the chance of filing a patent which was published in 2020, and since 2017 we have been working on this specific type of polymers, and we anticipate that for various applications, biomedical, pharmaceutical, but also in the field of agriculture, that some of those materials might make a difference in the future. Now, without going into all the details, I would like to highlight two key things of this material. So the material which we develop, this is the chemical structure, and the main part of the building block of the hydrogel is this compound, which is polyethylene oxide, which means that the material will take up large amounts of water if you put that in the body environment. On the left and the right, you have a functional group that can be polymerized, which means that if you put those polymers in solution, that upon the effect of UV reaction, that you can actually convert a solution into a hydrogel material, and that's what actually we make, or we use those polymers for in our laboratory since many years. Chemistry shown here, I will not discuss that in detail, but if there would be an interest to learn more about that during the conference and also after, I'm very open to discuss any further details. So starting from polyethylene oxide, we developed a series of building blocks for hydrogels with different molar masses. So the length of the polyethylene oxide was different, and we anticipated that for biomedical applications, that the mechanical properties, but also the release properties of different bioactive compounds could be tuned by actually varying the exact chemical composition, the molar mass of those compounds. And again, here we characterize the materials in depth through NMR spectroscopy, gel permeation chromatography to really prove that the structure, which I showed you in the previous slide, is the actual one which we are working with. Good, then a couple of material properties. So if we start from those building blocks and we cross-link them, then we can actually obtain different types of transparent hydrogels. And the aim of selecting different molar masses from 2000 to 20,000 was situated in the fact that if you look at the mechanical properties of certain tissues, that with some of those materials we can actually more or less span the entire range of mechanical properties going from blood vessels, cornea, kidney, over heart muscle to liver. So with one technology, we really hope that we can apply the material for a large variety of applications. And again, here a couple of other analysis techniques that were performed to study how well those materials cross-link into gels, how the swelling is affected by the molar mass. So typically, with a higher molar mass polymer, you obtain a higher swelling of the material. So a technology that enables us to carefully fine-tune the final mechanical and other properties. Good, that's the polymer technology. What I would now like to discuss with you is the second very important aspect, and that's actually the processing of those materials in 3 dimensions. And I will not take you through all of the requirements that a scaffold has to meet before it can be used in contact with the human body, but of course, biocompatibility, in some cases, biodegradability is an important aspect, and of course, porosity is a key aspect as it allows cells to attach to a material, to migrate through material, and that also waste products and nutrients can be transported in or out from the material. And what I will try to do in 3 different, or using 3 different polymer processing techniques, is try to give you flavor of what those materials can actually be used for. And the first technique I will shortly show some results of is electrospinning, some extrusion-based 3D printing, and then a very recent technology, which is the so-called multiphoton lithography, in short, 2PP, as we call that in our lab. And again, I have more slides than I can present here today, but if there's an interest to learn more about certain of those aspects, feel free to ask that either after the presentation or during upcoming coffee breaks. So first technique that we applied was actually electrospinning. In a nutshell, you start from a polymer solution, and after a complex process, you can obtain these type of fiber mats, which contain either randomly distributed or aligned fibers. And for certain medical applications, each of those architectures has their own benefits. Applications within the field of nerve engineering require aligned fibers. Many other biomedical applications require randomly distributed polymer fibers. So with this technique, electrospinning, both fiber geometries, morphologies can be easily obtained. Using our polymers, we have been evaluating whether or not they could be electrospin to produce those polymer fibers. And with each of the developed building blocks, after a long time of optimization, we could actually produce these electrospin mats in a reproducible fashion. And typically, if you talk about upscaling, at first you start with very small sample sizes, but nowadays A4-sized sheets and larger can be produced, which of course can be very beneficial in the field of wound dressing or any other application. Together with a local university here, we have been studying in an in vivo trial to see whether or not some of our materials can indeed stimulate the closure of certain wounds. And what we could show, as compared to a reference like Aquacel, is that our material heals at the same pace or somewhat quicker than the classical materials, the reference materials, and that no important signs of inflammation are present when these hydrogel building blocks are being developed. And again here, different types of materials were evaluated. If there's a further interest in that, we can easily continue the discussion later on. Good, then I move to the second technique, because with electrospinning you can only make polymer sheets, very thin sheets. For certain biomedical applications, you want to move one step further and you want to develop three-dimensional scaffolds, and we can do that through, 3D printing. So starting from a certain design, you actually use a printer like this one, and what you end up with in the end is a perfect replica, hopefully, of your original design. In this case here, we try to mimic the 3D architecture of a human meniscus using a polymer which is also well known to most of you, which is polycaprolacton, a biodegradable polyester. Good, we then moved to applying our hydrogel materials in this specific printing technique. And once again, you can see here different types of printing patterns, different types of pore sizes, different types of strut diameter. So it was for us not a big surprise, but we were very happy that after 1 or 2 years of research, that we could really show that the AUP materials that we developed enabled the successful and also the reproducible printing of different types of scaffolds. Those materials were intended originally for orthopedic applications. So we still hope, that in the long run, we'll be able to apply some of those hydrogel materials to replace human menisci upon failure. More on that later. So different architectures were being produced, and of course then for us it was important to see what effect that had on the mechanical properties. And I will just focus here on the graph on the left. You can see that one printing pattern has a certain mechanical property, Young's modulus of 2 megapascal, and if you change the printing pattern, you increase or decrease your mechanical properties. The main conclusion was the fact that only those two patterns come close enough to the mechanical properties of the human meniscus to really apply it in the long run. So that already reduced the number of samples. So this pattern was skipped from all further tests, and those two patterns actually survived the first stage. Next, we looked at how pore sizes and strut diameters affect the mechanical properties, and much to our surprise, these effects are much less pronounced as opposed to the printing pattern. So whatever you change in this range related to pore sizes or strut diameters, it's mainly the printing pattern that has a real effect on the mechanical properties. These are two movies. I think if it would be possible, can I do that via the, or perhaps if you activate it there, I will give a short explanation already. This was for us the final proof whether or not the first generation materials could make it to an orthopedic application. What you see here on the left is a test of a hydrogel material under a so-called material testing device. You compress the material, you release the force, which means that the water can have the time to actually again be transported through the scaffold. On the right here you see a dynamic testing device, and if also that one can be opened would be very nice. Thank you. So you see directly that the frequency is much higher, which means that these different types of setups mimic quite well what the loads are that a human meniscus implant would be facing. But of course, you also see that if you look at this finding here, that each of those scaffolds failed after less than 3,000 cycles. So long story short, those materials are not to be used at all in the orthopedic field. Very recently, 6 months ago, we found out that if you change the 3D printing technique from extrusion to something else, that all of a sudden you can increase the lifetime of those scaffolds with a factor 1,000. And at present, we're trying to see if that can still be increased to bring this technology also somewhat closer to the millions of cycles that such a material has to typically survive. I will skip for the sake of time this one, and I will focus shortly to finalize my presentation on the aspect of multi-photon lithography. So what you have seen, the first polymer processing technique was electrospinning, which enables you to make very thin polymer sheets. Extrusion-based printing enables you to develop three-dimensional scaffolds, which can be 1 cubic centimeter in size or even larger. What this two-photon processing enables you is actually to develop polymer features that have sizes which are lower than 1 micrometer. So that means that this technique as such will most likely never be used for developing entire scaffolds, but you can use this technique to functionalize scaffolds obtained through electrospinning or scaffolds obtained through extrusion printing. So you can use 2PP to write additional patterns on the first two techniques mentioned. Principles shown here, I will not highlight that. If there's an interest, I'm happy to further discuss that. But what I want to show here on the left and the right is, and that's for a different type of polymer which we also apply in our lab, is that by very small variations in chemical composition, that we actually go from polymers that cannot be printed at all using two-photon polymerization to polymers here on the right, which enable a very precise mimicking of the original design of the material, and completely similar data were obtained with our AUPs. Certain polymers cannot lead to stable structures. If you increase the number of functional groups at the end of each polymer, then all of a sudden your polymer scaffolds that you obtain are stable structures to be further applied. Good, before coming to my conclusive slide, perhaps a couple of collaboration possibilities that I really see possible when I was looking at the program before the start of today. Those materials that I described here today have not yet been combined with any drugs, whether it's synthetic drugs or any other bioactive compounds from nature. And one of the prime things to be looking at would actually to prevent the formation of biofilms on those materials after implantation. So a research line which we are not yet looking at, but where our research group would have a keen interest to develop that together with some people in the audience. So the aspects on drug delivery. I'm a chemist from nature, so artificial intelligence is completely out of my scope, but what I read and learn from it is that in the field of developing new polymers and also designing scaffolds, that really the steps which can be taken there to advance the field are enormous. And also in the field of micro and nanoparticle development, this technology has not yet been used. So if there would be an interest from anyone in the audience, I would be more than happy to collaborate on that. Looking at the timing, I will not summarize the different things I have been mentioning before, but I really hope that in this presentation that I've been able to shortly introduce to you what type of materials we work on. Hydrogels is one main focal point of our laboratory, and the discussion here today was mainly on orthopedic applications, but these polymers also find use in many other fields. So with this, I would like to thank Oana for the very nice organization of this conference. I'm really happy to be here, and I'm looking forward to an exciting 3 days and discussing science with all of you. Thank you very much. Mm-hmm.
Did you ever thought about combining, for example, collagen or hyaluronic acid for the new development?
Yeah, Good point. The project in which we are involved is a multi-step project. The first part is developing hydrogel-based materials as such. If you look at the anatomy of a human meniscus, you have these collagen fibers which are present there. So the combination of those materials with collagen, with HA and others will certainly be important. In another study working on tendon regeneration, we have been combining some of those AUPs with HA, hyaluronic acid, which actually gave very beneficial biological outcomes. So one of the next things to be done, what we tried to do in this first project, because this was the work of 2 PhD students over a period of 4 years, so time flies, is to move it one step further to try to combine it indeed with some biological aspects. In the long run, whether we will obtain also really applying a tissue-engineered approach, I think that's far away from now. That's why we go with this approach in a step-by-step fashion. But certainly a very valid comment and certainly with positive biological outcomes.
Thank you very much for a very interesting presentation. The entire presentation was very nice, but my attention was on the electrospinning process. I would like to ask you if we can electrospin just synthetic polymers, or we can make this also for natural polymers, or we have to split, or we have to combine them. Is there any rule for this?
Yeah, good point. Synthetic polymers are the most easy polymers to electrospin. Any student that starts in our lab, we give polycaprolacton, 80,000 grams per mole. They run to the lab and that works fine. From the moment you deviate from polymers that are perfect fiber-forming polymers, like some synthetic, but also some biopolymers, a detailed optimization is required. But having said that, in our lab, but also worldwide, polymers like gelatin, collagen, alginate, and others have already been spun as such. So that's good news. Now comes the main limitation. If those polymers are water soluble, then from the moment that you spin them from different solvents, from the moment you bring them in contact again with the water environment, quite often they again go into solution. So the main limitation, in my humble view, is the fact that you have to be able to cross-link those fibers after electrospinning. And cross-linking in the solid state is not always the most important aspect, the most easy aspect. And that's, as you mentioned yourself, quite often polymer blends is the way to go. So then we make a combination of gelatin, collagen, alginate with some synthetic polymers. And those synthetic polymers then trap also the biopolymer in the fiber mat. So I think that new chemistries to enable an efficient cross-linking after electrospinning will certainly be an important aspect to be looked at.
I have a question. It's a pretty long one, so I have to...
No worries.
You talked about the process of this type of polymer. So I want to ask, do this type of processes have any carbon footprint?
Very good point. The answer is yes. If you look at the process of electrospinning, just one example, you apply a high electrical field between an injector and a collector. Also, the further processing of those materials will certainly have an effect there. On this type of projects, we have not yet been looking at that in detail, although we notice that if we submit new projects, that quite often reviewers indeed start also addressing this question heavily. The second technique, the extrusion-based printing, will have a lower footprint for sure than the electrospinning one. But as I mentioned, the electrospinning only enables you to make thin sheets. Well, you can go to scaffold level, but with some other adaptations. But you need the extrusion-based printing to go to scaffolds. But if you need a thin sheet, then film casting, which is, I would say, having a lower footprint, or electrospinning are the ways to go. And with electrospinning, we didn't calculate it, but I'm pretty much convinced that the footprint is very large. Okay, you're welcome.